Okay. Thank you so much, Milita. Hello, guys. Thank you for joining me today. I'll cover. Okay. Let me confess. Of course, it was a clickbait. I don't know nothing about rocket science, to be honest, but I know something about teams that were building complex systems like rockets and something else, and I can tell you a little bit about that. Topic would be rather tough for unprepared listeners. Slides are poorly designed and jokes are silly. That's how I do things. But I try to, come up with good content actually to make you rethink the way you are thinking about product management as a discipline. I hope you can see my screen and I'll start right away. Okay, so there are lots and lots of different practices built around software product development. Me, myself, I'm a senior product development at a company called SIT Alimira, and I'm product manager for 7 or 8 years to now. And there's always an issue on how to choose right ones, disciplines and practices to use in the development in your company. What should be criteria? Is there theory of everything for choosing right disciplines to do software engineering and software development from the point of view of the product manager who is in charge of everything? Is there any basis for all those matters actually? That's all what I will try to cover in my presentation. And here's some problem right away with product manager's definition itself. Like, do you actually have the common understanding of what it is? Because from what I've heard, and I interview product managers a lot, in each and every company, product manager does different set of things. But usually it's considered that this guy can or girl can do it all, actually. From design mockups to calculating, data things. Let's say if you are going to become a mechanical engineer and work in a Formula One team or somewhere else, a nice place like Tesla, you'll have to learn 2 things at least. It's math and physics. It's a base. Math is an abstract level discipline operating with numbers and equations, and physics is based on the math in its calculations part, but it also has some domain-specific areas like predefined variables, constants, formulas, and rates between them. And with known just math and physics, theoretical physics, you can, after that, apply those applied physics disciplines that are built in the theoretical physics as a basis. So those are 2 bases that you actually should use if you want to become a mechanical engineer. In software management, there are lots and lots of applied disciplines like jobs to be done, use cases 2.0, customer development, Scrum, Kanban, you name it. And my question is, product managers, what is our physics? Where is our theoretical physics? What can we consider one? Where is the base for all those plugin practices? Because if we don't have any base, then we cannot communicate the same thing we intend to. We cannot, discuss it because we have difficult common ground. We had different ontologies in our heads. So no science can be based on it. No research, research concerning the product manager's area of operations. So no cookies for product managers after that. My answer is, and as long as I don't have a better one, it's systems engineering. What you see here is a V diagram representing system lifecycle. The steps system should follow to become an operational product as it intended to be at the start. It's rather complicated concept, and it's just for illustration purpose here. So I'll move along. Why? Why the system engineering appeared in the first place? Okay, let's see some numbers. It's not a secret actually that most of the product management and product development practices are originated from military scientific projects happened since mid-20th century. So let's see what system engineering can offer in terms of complex products. Modern car has 15,000 parts and can drive right with a 200 kilometers per hour speed while being stable and safe. Okay, this is not modern car, it's a Volkswagen Golf, but it's a really pretty picture here. Airbus A320. It has 340,000 parts it's combined from, and it currently takes 8 months. What can it do? It can fly at the 10,000 meters altitude with 150 passengers on board and take them whenever they want in 2 or 3 hours. Okay, another one. Aircraft carrier, Queen Elizabeth class. It has around 1 billion parts and it takes a size of a city block. All those products should follow through difficult cycle. It should be designed, built, maintained, sometimes decommissioned and disposed of that. And supply chains of unthinkable complexity should be organized to embody those products, to build the factories that can build those products, which is even bigger task to do. And during those projects, lots and lots of issues will emerge. Lots of risks will be identified and possibly addressed. And system engineering was invented and implemented exactly for such cases, to prevent bad design decisions for complex projects. Let's see at its efficiency. It's some statistics of the system engineers. I'm not sure if it's entirely true and we can believe it, but still it's something. So systems engineering was initially used to deal with the complexity of aerospace projects in NASA, in the Soviet Union, in America, United States. And it was extremely effective there because for small projects to meet deadline and budget, it was necessary to spend 5% of the project's efforts on system engineering, which prevented a possible increase in project cost by 18%. It can be represented here, like blue bar is a total cost of the project, 100%. Green bar is a spending on the systems engineering, and red bar is if we didn't spend those budget on systems engineering, then we get this increase in costs for the project. So you can see that for very large projects, increase in its budget will be almost 2 times, and it might even, it might even end the project here. It can be dead at the moment because there are not a lot of companies willing to budget 2 times more than they wanted to. So basically, system engineering, as a conclusion, was needed to make large and complex projects cheaper. It allows you to save money and efforts on the rework of poorly designed decisions, and allows you to cut off set of risks in advance because it knows that there are risks, and it can guide you through this decision-taking process. So let's dive into some historical perspective, shall we? Age of discovery from 15th to 17th centuries. That's when the big European empires, developed European empires, started to discover everything in the world. Some standardization of how vessels, ships, and crews should be constructed and organized were provided. And this type of standardization, even poorly executed, provided European states with capability of taking over and controlling their colonies and taking resources from it. It became a business model for them. It wasn't a business, of course, it was more of a royal matter, but still. But first, capitalist entrepreneurs appeared in 17th century. They were not guys of a noble kind or royal, heirs. but there were people who made the money out of their entrepreneurship skills and efforts. In the middle of the 19th century, as a consequence of consolidation of resources, there was a big surplus of money in the Europe. And this money, it should be managed somehow. Concept of money as a capital actually was established. It should be managed somehow, and management and administration schools, which we know up to the day, actually appeared. Before that time, no investment concepts were used as a driver for commercial endeavors, because it was mostly companies, large companies that can do, this abroad business like a colonial one. They were all state-owned companies, and all investment decisions were taken like, what do you mean you're out of money? Go and take some from treasury, come on. No one was, trying to calculate return on investment. That wasn't an issue at all. But after this middle of the 19th century, projects started being considered as an investment for capital growth rather than just royal will to do things. Then we go to the beginning of the 20th century, where the administrative efforts starting to emerge. Railroad companies, which were big and they had a lot of employees, distributed across the entire country, came up with the remote control methods. They used standardized paper forms to fill and file cabinets. And that was, enough to make a big enough step to compete and win against the smaller businesses. In the 1920s, first approach to project documentation emerged. Constructor and design drawings were standardized so that they can be used without its author to, give you context about these drawings. You can just learn how to read it and build whatever is on this drawing, like door out here. It's a real drawing from this time, actually. And project and design documentation became verifiable so that you can tell just by knowing how to do the right drawing and looking at the poorly executed drawing to say that it won't work, actually. Of course, Ford and scientific approach to management appears in that time. Henry Ford came up with the idea of producing a product. Familiar word, isn't it? A product, a generic thing that could be produced and sold in large quantities. Assembly lines were not the only key to Model T success. Also, it was the standardization, unification, and the development of inline production in big scale. And also transfer of technologies becomes possible because everything documented is standardized. Ford moves its production lines to distant plants, some of them even across the sea, and still handles it. Okay, after that, design documentation became a formal representation of entire production process, and designers and guys who were making those drawings and those designs were able to work without even spending a day in a factory shop, which was unthinkable before, because you needed to give explanations on your drawings to the factory shop workers. Of course, next big leap comes during the World War II, when lots of companies needed to produce complexes of products. What is complex? Complex is when you take a plane, like plane, airplane, military airplane like here, and you put a machine gun on it, or you put 2 cannons on it, or you put a radar system on it, or something else. And all those systems should be interconnected in an understandable and explainable way, so that you can come up with whatever configuration you need. So pictured here is B-17 bomber. It was available in 39 different configurations and was produced in thousands. If you want those bombers in such amounts, in such number of configurations, you will need to produce and deliver right number of correct parts. You'll need to deliver them. You will need to assemble them in the certain configurations after that. That requires from you practices of system composition and configuration management, version control, engineering change management, and so on. So the complicated disciplines of how to handle such kind of difficult supply chain, they were created, invented, and implemented. The idea was that behind that, that no single head of even genius engineer can actually enclose an entire project or program of project scope at once. So it should be parted in, not head the project, it should be parted into smaller projects while keeping intended goal at focus, and so that the parts are connecting with each other the way it's intended. In 1959, project manager article by Paul Geddes from General Electric appears in Harvard Business Review with the statement that in large project, like military airplanes, a new role should appear. Not designers, not engineers, but project managers will be responsible for the implementation of the engineering concept, the economic side of the project, all aspects of design, manufacturing, construction, and everything. And all designers and engineers should be his subsidiaries. From 60s to 90s, program management and system engineering evolved with the great assistance of the computer technologies. System approach 1.0 was followed by 2.0 in the 90s, and 3.0 is almost here already right now. System engineering were used to launch NASA space shuttles, design and build nuclear plants and aircrafts and aircraft carriers. It was described as in a big set of industrial and military standards and so-called Systems Engineering Book of Knowledge, SEBOK for short. Software engineering, which I am part of, was in its turn part of this bigger picture, because it still is, because software doesn't exist in vacuum. It's used in the physical world, with physical people and physical things around. And knowing some basics of the systems engineering will give a lot of heads up for software product managers. And by the way, if you want to see how projects were made during those golden years of engineering, you can read this book. I've read some summary from it. I didn't get book yet, but it's phenomenal. It's about how a guy with not enough resources and manpower managed to make a jumbo jet that saved Boeing at the time, Boeing as a company. Okay, then we should dive in a nutshell. The systems engineering and thinking in a nutshell. Subdiscipline of system engineering, telling us how to think in terms of system approach, is called system thinking, and I'll cover only this one in this presentation because I don't have more time. Its goal is to install this new way of looking at the product and system and project to the person in charge. So this is the essence of system thinking by Anatoly Levinchuk, one of the authors of the book, which is in the base of the course I've been studying. So to satisfy the needs of external stakeholders, one must understand the operating principles and possible design of the supersystem, and thereby formulate functional interface requirements for the target system, and so on. I believe you've read it already. This is the essence of what systems thinking is. It's almost a huge step process described here, which has a lot of details, of course. So we can see that there are major concepts in this essence thing, which are stakeholders that can be external or internal. Supersystem is the system which we are building in as a subsystem. Has its operating principles, possible design, target system, which is our system, the one we make, has requirements, architecture, design, subsystems made by our team, and so on and so forth. And system life cycle practices is the things you've seen on the V diagram. Let's dive into details. Okay, so system definition realization. System is existing in the real world. That's the first axiom of the system engineering. If you can touch it, you can, knock on it, it's not a system. Here you can see two things: table as a system, it's a wooden one to the right, and table definition or description on the left, which is an instruction to how to assemble this table. To the left is not a product, to the right is a product or system. Because we believe the system takes some volume, some place in this our space-time, accepting Einstein's idea about existence of a physical world in our four-dimensional space-time. So if we can knock on it, then it exists. If not, it's not yet made or doesn't exist at all. System definition is a conceptual understanding of the real system. So it can describe the system in some way, and it shouldn't be confused with realization. Common case for such, sometimes, even usually I'd say, developers consider the source code to be a final product of their work, but it's not. Let's say if we have software to calculate taxes, then source code has no use for us because it only becomes a system or a product when it's calculating taxes and doing some outputs out of that, and some decisions are taken by someone based on these calculations. It also requires a desk to place a computer to run this program made out of this code, and most certainly the operator who will do the calculations. So again, it's not a system source code, but system working in its operational context is a system or a product. System definition might differ greatly depending on which stakeholders' concerns are we addressing with it. System should be described with at least 3 breakdowns. Functional, pictured here, like how it works, what should it do? And product or modular, what is it made of? What are its parts, like modules, back and front end database system and so on. So what it's made of. Okay, there are 2 diagrams. To the left is functional, how it works. To the right is modular. Can you actually tell which product does it describe? Which system does it describe? I'll give you, a couple of seconds. Sorry, because we're behind the schedule. So it's a scissors. It's a scissors, and in terms of functional breakdown, it has knife block to cut and handle to hold it with my hand and apply force so that it can cut. But in terms of modular breakdown, it has only 2 halves that it's actually made of. And if we will confuse one with each other and give this functional diagram to the guys on the factory, they will say, okay, we will give the knife block to make to someone who makes knives, and we will give the handles block to make to the factory who makes handles for the furniture, because they know how to do that. And of course, they will not come up with the scissors. So there are two major system breakdowns we should have. Second big concept is stakeholders, also known as project roles. And in system engineering and system approach 2.0, stakeholder is not a person. Before system approach 2.0, it was believed that system produced by the project team was objective and understood by everyone in the same way, unambiguously. And of course, it quickly became a fact that it's not correct, and stakeholders concept appeared after that. Stakeholders usually confused with the real people performing their role in a certain project, but it shouldn't be, because stakeholders are real roles. It's a project roles that some people play. One role can be played by several people. One person can play several roles at a time, or one after another, and so on. Stakeholder, yeah, you can see here that Mike Myers actually played two different characters in the same movie with different interests that were actually antagonists to each other, Austin Powers and Dr. Gravel. So as well as that, people can play different roles in the single project. Each role in system approach has three things it's associated with. It's a subject of concern, it's a preference, and it's intention toward this preference. I'll explain this a little bit further. There are three basic meta roles that should be in any project. Entrepreneur, who is about what we do and for whom and where to take money. Engineer, who comes up with a system that we are making, target system. He makes design, construction, implementation, verification, and maintenance of the system. And manager, who is managing the team efforts for making the product real. We can check the simple case, like if I'm a freelancer making simple landing pages, that I have all three roles at the same time. As an entrepreneur, I'm looking for new customers and negotiate the conditions. As an engineer, I do design and I implement the said landing page. And as a main manager, I manage myself and my time to do that on schedule. And another case, when let's say I'm one of the marketing division of a large vendor and I'm in charge of organizing events and their publications in some region, let's say in some town, even though it's marketing division, my major role is not even entrepreneur, even because it's marketing. Still, it's manager, because I don't work with external stakeholders to do some entrepreneurial things. I just perform the plan that was given me from above. So in this case, I only play a manager's role as well as other marketing managers in other regions. External stakeholders and roles are ones outside of the company, the ones that want some system to be made, and team roles considered internal. Any project should have at least 15 external and internal roles. In my research here for academic conference software, long list of roles had 44 roles. And software system can play roles as well. System levels is another major concept. A system is considered a hierarchy, like it's made out of system levels, columns, each of which is a system containing other systems inside. So system itself is built into a bigger supersystem, and it's built into even bigger, and it ends somewhere with the universe. We can see those as a different levels as pictured here. This way of decomposition into smaller parts, or composition of the same level systems into a supersystem, usually called system breakdown. It's inherited from the classical biology, organisms, organs, cells, molecules, and so on in both directions. There are some examples of how you can make a system breakdown. Mastering the system level concept is crucial for mastering the entire systems thinking. And when we talk about systems, we actually talk about 5 types of systems, which are super system, which should be considered first because it's the one that will come up with the needs that will become requirements towards your system. So it should be studied and analyzed before everything else. Sorry, I'm kind of, yeah. Operational environment systems out here. It's in the yellow. Those are systems that exist on the same level as our target system. And altogether, they form this systems level below the supersystem. Other reason why it should be, we should care about this systems in an operational environment is because our system alongside with other systems of the same level must come up with the so-called emergent property. It's something that didn't exist before all those systems got combined. Like, you know, metal disc and rubber ring just lying separately can't provide cars capability of moving and maneuvering at the speed of 200 kilometers per hour. But when you make it into the car wheel, then it actually can provide this capability. And this enabling system here to the left is actually our team making the final product. And our target system, the one we are making, consists of the smaller subsystems on the lower level. So those are actually basic concepts of the system thinking that we just covered. We didn't cover system models, requirements, architecture, system practices, and everything else. System thinking actually might be considered as a big system of checklists of things you should check one by one to be sure that you are moving in the right direction and you are not doing bad design decisions about your system. And checklists, as we know from the book called Checklist by Atul Gawande, checklists are saving from catastrophes with the bureaucracy. So here is a system thinking checklist, things that should be considered on the top level of the practices about each and every system and product you are doing or making or anything else. And we're jumping to a conclusion. System engineering and system thinking not really needed when you do something simple, like in my example, landing page and your own, when you're a single person on the project. But with increasing of the complexity of projects, even simple at first glance web app like Twitter, like has lots and lots efforts behind it, and may require some of the described practices and ones we didn't cover. And what's best, it can be used as a project manager's theoretical physics from the beginning of our presentation that can be applied for two major things: quick understanding of the details of any project you're in, and choosing from applied disciplines and practices to install into this very solid base. So my conclusion is system thinking is a good candidate from my point of view to become common ground for big products and projects to consider, to be considered by product and project managers. And I think I should finish at this one because time. Am I correct?
Yes, we have 15 minutes more for questions, and maybe
if we don't have any questions, yeah, I have something else. But if we have questions, then we can discuss those. So, guys. No questions so far, I believe.
Yeah, okay, we have one in the chat.
Okay.
Okay, Slavko, would you like to talk with us, or you want us to read questions?
It's fine with me either way. Basically, the question is, this approach, as you said in a conclusion, it's not for modern projects, landing pages, etc. So it's mostly about mission critical systems where the high precision and high dependency is really of value. But even so, in the modern times, how do you, first question is, on your slide, the validations come on the right side and it looks like they are on the end of the cycle of things.
Let's check it. Okay, yes, yeah. Of course.
So is that necessary? Basically, can we do them in parallel, more respective on the levels of them? Because yes, of course, system validation, we can validate even when the system is done, but component validation, component verification, etc. Can we do it in parallel and still maintain this high precision, high dependability, etc.? Second question is, in modern times, you still need to sell this approach against all these modern lean, flexible, and move fast, break things approaches. And there is a third question. I did not have time to type it, but basically, how do you keep complexity from becoming a complication, dead weight, and basically something that slows you down and becomes obsolete at the end of the cycles, or even more critically, from becoming system design flaw. Talking about F-35 jet fighter, for example, really complex system, but at the end, like a month before they needed to launch this airplane, they could not get it up in the air. And there is this story about the passenger planes with system flaws, like failing in some detections, etc., etc. So these are also mission critical systems, taking a long time to develop, but still we can see the pressure from the market to not keep this SE approach all the way. So
wow, that's a long one. Okay, thank you for the questions. I'll start from the beginning, the two you've typed in the chat. So validation strictly at the end of the cycle, of course, because cycle is cycle and it has its logical stages, but the duration of the cycle, the size of your cycle should be defined by you as a product or project manager. So you decide whether it should be half a year or should it be 2 weeks to have cycle, or on something small that can be validated easily. So basically, represented life cycle here has let's say logical time frames, not real time frames. Like it's not weeks or months or something. It's just logical steps that you should perform to be sure that you've made everything to consider all the things should be addressed. So basically, agile is applied here as well, because in the end of the sprint, if you take a classical Scrum like we have in our company, you set the sprint goals, and at the end of sprint, you validate those goals. Are those actually achieved or not? What can we do about that? So the answer is validation strictly at the end of the cycle. Yes, it is, but the cycle itself, what it should consist of, and the cycle duration should be defined by the team. So it can be moving fast or it can be moving really slow. It's up to the team and the way it has chosen the framework or the method of the working. Second, how do you sell this approach against modern, inflexible, move fast, break things approach? Same way, because systems engineering and system thinking is merely a checklist that can be applied to any kind of the framework you're using. Some of the practices you can leave them. You can not use some practice of the system engineering because they might be too overcoming, too cumbersome for you at the moment. If you are not building an aircraft or something else, then of course you don't need all the practices. You should take only those that will make your team stronger and faster. And the third question, could you please sum it a little bit shorter?
How do you keep complexity from becoming complication, basically? Yeah. So because there is a difference between complexity and complication, right?
Yes, complexity is usually described as the number of elements and the bonds between them, right? Like we can represent complexity as a graph, so the system engineering itself and its system breakdowns is the way you actually isolate graph parts from each other and organize them in some number of concepts or contexts that are tied together, but can be worked out or described as isolated parts. It's it's a usual use of typical analysis tools when you take something big and you somehow, with your attention, somehow you dissect it into parts and then you study each part separately. So that's the only way the humankind, came up with complexity solving problems, and that's the way systems engineering does that.
Cool, thank you.
Thank you so much for the questions. That were deep ones, actually. Another ones? Do you have anything else? No. Okay. If we don't have any questions, I'll just jump to my final 2 or 3 slides I have. If you want to catch something a little bit simpler than we've just covered, which is tough, I know that, because I've studied that for 2 years before I was managed to actually apply that. You can take out of this presentation a single thing. It's a model called OMG Essence, alpha states diagram, alphas diagram. It can be considered a system project model applied to system engineering, and it's actually quite easily to grasp at a glance, because it still uses our 3 big roles: entrepreneur, engineer, and manager. Each of them has 3 areas of concern, let's say, of interest. And alphas represented here are abstract level things that are existing in any kind of project you might face. There are no projects where some of the things are not present. I'll just name those. Stakeholders are the same things we've covered. Those are project roles. But here we mean external stakeholders, because internal ones are here in the team alpha. Stakeholders identifies some kind of opportunity for a project to happen. Opportunities are other alpha. It can be represented by business plan or budget or something else. Some change in the world that made this project possible, because before that change, project was not possible for some reason. Like some company now has a budget for CRM system and we can build one for them. That's kind of opportunity. Then the opportunity focuses requirements for us, and where it's engineering part of a project, requirements that should become software system in the end. So we are working with those requirements, we're collecting them, we are checking them, verifying them, and so on. After that, those requirements become the basis for work. Work is a real work that happens in the real time when you write code or you do other kinds of tasks, like maybe quality assurance, or you're writing your requirements down, or you are interviewing someone. This is described as work, which should follow a way of working, which is basically a technology we use, frameworks we use, and the software we use. Way of working is applied by team, and team performs work. So this blue area is area of a manager, and his duties out here. He should manage works, way of working, and team. And team, of course, team produces software system that should be verified by engineer and then validated by stakeholders. Stakeholders use system and pay you money. It's the top layer of this OMG Essence framework. You can find lots and lots of explaining YouTube videos how to use those. And inside, of course, they're more complicated. It's a meta model because we only touched alpha, and there are alpha states that, like, each alpha has its states moving to the end of the project. Each alpha has a work product. Like if we say alpha requirements, then the real work product is, let's say, table in Notion, where all my requirements are actually listed. So work product is some kind of realization of alpha, and so on and so forth, up to the competency, activity, and so on. And you can build, and you can reflect any kind of framework with this scheme if you want to. they have really good card system, simple one, which will help you to evaluate what's happening with your project when you should, vote for which state each alpha is, and you can use some kind of gaming cards for that, so it's not boring meeting or something. Those are my references. I think organizers will share the slides deck, so you can use the links. If not, you can write me. You can contact me any way possible. I didn't state here once. It's a bummer, but still, okay. I'm Artem Ushanov. I'm on Facebook. I'm on Telegram, wherever. Thank you for your attention. Thank you for your questions, and I hope it was useful for you.